Good evening. You all are joining me for this volume complexity video. I am Mr. Thank you for joining me. We have looked with regards to rotational dynamics, where you are rotating a curve around an axis. We have looked at the disk method, the washer method, and the cylindrical shell technique. With regards to this volume complexity, there are situations where you can have a disk and a washer develop in the same solid, in which now you have to then rely on this mixed technique. The complexity is the fact that you have to rely on this mixed technique. Take for instance the example we will look at in this video. It'll look like this. You have a function, a linear line extending upwards. The rotation will be around the y-axis from a domain 0 to 1. If you were to limit this domain in this enclosed region, and you're looking at this area now within these appropriate curves, you rotate it, you develop your solid, which will be an interesting solid. We can just draw it out right over here three-dimensionally. You know, you have this primary shaded area, and then you have the rotation developed. You have a closed cone which develops, and you're looking at a solid of this form. If you were to take a cross-section from right here and pluck it out, you know you'll have a cross-sectional slice reminiscent of a disk, through and through solid. But if you were to peek up above here and now take a slice here, you will have a washer develop, and that right there is the complexity that arises within this same solid, rotational solid. We have two forms showing up. We have a disk, it can be with a C or a K, it doesn't matter, or a washer and a washer. Actually, both of these slices show up. So part of the domain is affected in terms of the disk, the other with the washer. So how do you go about doing this? In this video we have now presented what the problem is. We will solve the problem using the method we can with this mixed combination technique, and then at the end of the video I'll show you your shortcut alternative to deal with situations such as this. There are some situations where the basic washer and disk method tends to be more difficult and you go to that other technique. And there's some situations where the other technique tends to be difficult and you come back to this technique. So they both can alternate based on your situation. So let's examine this specific problem and see how we can solve it using this mixed disk and washer method. So that right there represents our problem. We have a curve y is equal to x plus 1. You know, when you do x plus 1, you have a 0, 1. Y-intercept, you have a minus 1, 0. X-intercept right here. This point here can be represented by 1, 0. This point right here will be 1, 2. Why is that 1, 2? Because when you put 1 in here, you get a y value of 2. We have another equation, x equals 1 right here, vertical line, and here's our linear line. In essence, we're seeing a domain here along the x-axis, 0, 1. That's along our x-axis. But if you were to evaluate the domain here along a y-axis, technically you're going from 0 all the way up to 2. So you have these two specific items. The rotation is around the y-axis. We're essentially, as I've shown you already, looking at this area right here in quadrant 1, and you're rotating it around the y-axis. How can you go about solving this? You have to essentially set up two integrals. One integral will cover that portion of the volume which will be represented by the disk method. The other integral will represent that portion of that rotational solid which will cover that washer which develops in terms of the cross-sectional slice. How do you know what develops? Well, you start first by looking here at our rotation y-axis. If you're doing integration with respect to y, when you're doing volume determinations, you're going from a lower limit upwards. You're doing things along the y-axis, and you are looking in terms of your areas xr minus xl, because these will feed into your area y, which will integrate across your interval. You have to think about things in terms of xr and xl, right boundary and left boundary curves. So these curves have to be adjusted. Y equals x plus 1 becomes x is equal to y minus 1. The other equation, x equals 1, stays as is, and these are our two equations adjusted in this format. What you have to now do is determine where the disk is forming and where the washer is forming. When you look from right here, because here our intervals are from lower limit to upper limit along the y-axis, when you look from right here 0 and you look across right over here up to 1, 1, from this portion to right here, you know the disk will form. But from 1 up to 2 in terms of the y-axis, the washer will form. So we have to now set our intervals. Along the y-interval from 0 up to 1, these are just intervals in terms of y-axis coordinates. We have the disk method which forms. And here when you look across from your line of rotation outwards towards this x equals 1, we know our radius is exactly equal to x equals 1, which is our radius. That's our radius at that point. When you look at the y-axis interval from 1 up to 2, what we have now is a washer, but when we have washers over here, the washer will develop in terms of the cross-section. Now you have to think about inner radii, outer radii, inner area and outer area. You have to determine all of that. When you go from this point upwards, when you go across here, you have an inner radius, and you go across here, you have your outer radius. The outer radius here is just your distance from your x equals 0 to x equals 1, and that's just a 1. And the area, again, with that, it's always pi r square. Here it'll just be pi 1 square, which is just a pi. When you go from this x equals 0, which is your y-axis, your rotational line, and you look across to that curve, then that curve happens to be your inner radius, and that is x equals y minus 1, or just y minus 1. And this radius goes to the area formula, pi r square. You get y minus 1 whole square pi. Now you have your inner area, outer area, all of which can be used for that portion of the solid which is affected by the washer. And you have this right here, x equals 1, giving you an area of just pi for the portion of the solid which is represented by the disk. And now you integrate this in by means of two intervals. Your overall formula is this: from an interval of 0 up to 1, you're using the disk method, and here you have a pi and dy. Then we'll add to that interval from 1 to 2, everything here is along the y-axis. You will have an outer area minus an inner area, and you have to do this inner area calculation. We can bring out the pi, but for time being, let's bring the pi right over here. We'll have to open this up, and you have this outer area minus inner area, outer area minus inner area. You have 1 minus, that's my outer area portion, separated from that pi, and then the inner area is y minus 1 whole square, which is y square minus 2y plus 1, all with respect to dy. This right here represents my integral for this volume, one part represented by the disk method, the other part represented by the washer method, outer area minus inner area, everything with respect to dy. And now we have to just compute and take this to completion. Again, if it wasn't clear, let's blow everything up here. My curve is this. Here's my x equals 1, here's my x equals 0, my rotational line, and here's my, well, we'll write this in y minus 1, which is x equals y minus 1, or y is equal to x plus 1. From right here to right here, we're only seeing the disk method show up, and we look across, and here's my radius, which is just 1. From right here up to this point right here, which is 1 comma 2, here's my 1 comma 1, here's my 1 comma 0. From here to here, we're seeing a washer come into play. We'll have an inner radius, we'll have an outer radius, which will lead to our inner area and outer area, and that's why we have broken things up into two integrals. And this right here represents the complexity, the mixed disk and washer technique. Let's integrate this. The first part, bring the pi out, you have a 0, 1 dy. Second part, bring the pi out from 1 to 2, you open that up. When you open this up, the ones will cancel out. You'll have a minus y square plus 2y dy. Everything here is polynomial integration. You'll have a pi here with regards to 1, pi here with regards to y, upper limit 1 and lower limit 0, plus pi here. You'll have a minus y cube over 3 plus 2y square over 2, which is just a y square, from 2 to 1. This will just generate you a single pi. From here you'll generate, really you'll have a minus 8 plus 1 is a minus 7 over 3 plus 3, because you'll have 2 come in here, which is a 4, and a 1, which is a 1. The difference of those two is a 3. You just have to take this to completion. Volume with respect to y of this rotational solid I showed you at the very beginning is equal to pi plus, you have to do this fraction algebra right here. You have a 9 minus 7 is a 2 over 3. You're seeing a pi plus 2 pi over 3, which is basically a 5 pi over 3. So the volume of that rotational solid I showed you at the very beginning is a 5 pi over 3. So we've presented what the complexity was. We've shown you how we can use a mixed disk and washer technique to solve this. Now for the third part of this video, I'm showing you what your shortcut alternative is. The shortcut alternative for this is the cylindrical shell technique, and let's look at it. You'll see this question here particularly will be solved very easily rather than this elaborate setup. Now for the conclusion of this video, we show you how the cylindrical shell technique comes and saves the day, and I will show it to you. Remember, previously we've seen the derivation, everything had to be with regards to dy because our rotational line is a vertical axis. But with the cylindrical shell technique, I've talked about that flip phenomenon. You always draw your Riemann rectangles parallel to your line of axis, and that's exactly what I'm doing right here. You look across from your line of axis in a perpendicular direction towards your Riemann rectangle. If that perpendicular direction happens to be along the x-axis, then you know you're integrating with respect to dx, and that's what we are. The height of these rectangles in this instance are yt minus yb. See, yt minus yb, we're looking across in an x-axis dimension. You know the volume here will be with respect to x. Since we're looking here along the x-axis, our integration intervals are 0 to 1. And let's do it from 0 to 1. We have to determine the circumference component. We're looking across in an x-word direction. Radius is equal to x, circumference is equal to 2 pi x, because you know the technique requires you to have the circumference, the height, and the thickness here, dx, all of which is integrated. Circumference, height, and your thickness. And we've gotten our 2 pi x. Let's bring the 2 pi and we'll bring in the x right here. Now let's determine the height component, yt minus yb, x plus 1 and y equals 0. So it's just x plus 1. That's the height of the rectangle. This curve right here minus this curve right here, yt minus yb, x plus 1 with respect to dx. The only reason why this rectangle covers everything and there's no split up of integrals based on where you are, like how I was showing you with the discs and the washers, because you're looking at everything here in a vertical orientation, and any of these rectangles from this point all the way to this point will always be affected by this curve on the top, and it'll capture everything in terms of washers and discs. It'll automatically capture everything. Hence the cylindrical shell technique for this instance is very easy, because it automatically captures where a disc is and where the washer is forming. You just integrate this. You have a 2 pi and you open this up. You have x squared plus x dx. Simple polynomial integration. 2 pi, here you have x cubed over 3 plus x squared over 2 from 1 to 0, which is just basically looking at 2 pi times 1 over 3 plus 1 over 2. You know you're looking at a 2 pi, and 1 over 3 plus 1 over 2 is a 5 over 6. Cancel these out, you get a 5 pi over 3, the volume with respect to that rotational solid. We know we've seen the rotational solid at the very beginning. It was an interesting little solid looking something like this, and we're giving a three-dimensional nature to it, and it was something like that, with an open cone here on the top, closing down right here, and the rest is all discs. Across in one part you had the discs, and on the top part you had the washers develop, and that right there was our basic rotational solid. Initially seeming difficult because we had to use a mixed washer and disc technique, but along comes a cylindrical shell technique and saves the day. In this specific instance, the cylindrical shell technique saved the day and made everything easy, but there'll be some instances where this technique will be hard, and then you bring the washer and the disc method into play, and that saves the day. But in this specific video, the theme was there is a certain complexity in the solid where both discs and washers come into play. And in those instances, the mixed technique is difficult, but the cylindrical shell technique makes it very easy. And that's it for this video. Thank you for watching. Have a nice day.